I hope to end at latest 6 o'clock, let's say, other people not too late. I suggest the speakers to put yourself in the front because it's you who have to answer, it's not me. So, are there any questions from the public?
Yes,
please.
Is this design tool ready, or are you still working on it?
We are still working on it.
You are working.
Yes. So it's the end product.
I suppose it will be available on the website.
Yes.
This is the procedure for Horizon 2020. You have it available. So, so you are in the 4th year of your project.
We are starting the 4th year after the summer.
Okay, so it's still early to have it ready.
Yeah, and the goal is that we develop a new REHVA guidebook. So there's a REHVA guidebook.
A new one, not the old one.
Yeah, so a new one that focuses more on the designing and operation of hybrid geotabs, because the old one basically introduced the geotabs concept.
Descriptive.
Yes, and we want to go more in detail on how to actually design such a building.
And one more question. Do you consider foundations and foundation walls?
Slab heat exchangers, you mean?
Yes, as tabs.
No.
Do you take them into consideration in your project, or you work only above the, let's say, ground level?
Yeah, yeah. Also the ground level, but that's then the bore field. That's closed heat exchangers, which are typically the U-tubes in the underground, not in the slabs.
But not foundation piles, not foundation walls, you don't take
are not included. They are included in a geotech project.
I know.
Okay, you can have a look there.
But the focus of the project is not so much on the different types of ground source heat exchangers, it's more on the integration of a ground source heat exchanger. The main focus is on double loops, but the integration of ground source heat exchanger, control, taps, and the hybrid, the secondary system. So.
Last question.
That would have an impact on the cost evaluation and the assessment, but then it should be changed afterwards. Price database.
Last question. How do you persuade architects to implement such solutions in their masterpieces?
In the masterpieces?
Masterpieces.
Masterpieces, okay.
Space utilization might be relevant there. The fact that you don't need to put
I mean,
radiators.
because usually architects are pretty reluctant to any, let's say, integration and working together with structural engineers and mechanical engineers and HVAC engineers and so on.
Maybe
so
I can give you.
Persuade them to
I can give you some practical information. When we had the discussion with architects during a real commercial project, it's not research project, but commercial project. So the thing is that when we get the customer, for example, we want to build a building that is the office. Then of
you
course,
go to certification.
Well, that's one important step. But your question is more about how to convince the architect, the artist. So one thing that we
very good point.
So because I guess we all have an engineering background, so we focus on different
architects.
Well, I would introduce a little bit more because it's like two people, they don't know each other, but we need to understand each other's values. So what do you put priority on your work? What do you like? What makes you excited? So for engineering, we take a lot discussion on efficiencies and energy savings, sustainabilities. Of course, this is important for architects in their career development in order to have your design that is sustainable and fits the certificate, for example. But the thing really makes them, horny, is that is that my design is very clean and very innovative. And they don't like, we have this discussion many times, they don't like pipes, they don't like vents, and they don't like seeing all these radiators around. This will kill their interests. So taps has an advantage that you put the pipe, it's hidden. So when you come to a room that is in in the morning session, I put the picture that how a TAPS building looks like, the moments when architects come into. So basically, it's just a space. Now you can have all your freedom to decide how you want the things, especially when it comes to different things that, for example, TAPS buildings, in reality, there are a lot of glazing areas. So architects wants to play with the light. So this is very important. And in TAPS buildings, actually you can achieve this rather than conventional buildings. And another thing is that when we cover the wings of the buildings, you have different geometries. And TAPS can also provide different solutions when it comes to wings. So you can have different orientations and the shapes, and this makes them feel a bit happier. And another thing is that we did the test in a commercial building in Germany that the building was designed with 8 stories. But when we have TAPS and with limited ventilation system, you can have 1 more floor. So in the end, it's 9 floors.
Yeah, but even there, an architect who is really reluctant could not be convinced.
Yeah, of course.
So
there are always discussion, because even though the architects accept the TAPS ideas, and there are a lot of coming back and forth. No, I want to, it's not easy, but this is a business, and it's applying to every.
I think you have a menu of about 30 issues that you can use in the first discussions with an architect to convince him.
Is it a deliverable in this way?
No, but I can make it if maybe I write a book. But it will be somehow also inserted because it's a very
6.4.
6.4.
True.
Actually, in context of the business model, we are looking to the values.
Yeah.
And another one is the more limited utilization of space for services, not only in the rooms but also in the technical rooms. So we actually have this.
Yeah, but it will not be the prosa that you can use in the conversation.
That's why we need people and not.
I think in the former one, in the descriptive one, there's more.
Explanation.
Like okay.
Yeah.
Yes. They might have been distributed because my contributions were in each chapter a little like okay, so you'll have to gather them together, and you'll find a lot of them that an architect will understand. Yeah.
Yeah. What is the stage of your design? In what stage are you now? Sorry.
So basically, at this point, we have the simulations for the office buildings done, more or less. We have a splitting algorithm that then processes the heating and cooling demand, taking into account the design of the taps, the desired comfort range and things like that. And so we have analysis of the costs, and we are now in the process of bringing everything together and being able to do the clustering towards more simple rule of thumb.
Because you know, Uponor is when it's tested a lot.
Yeah, we have to do sanity checks also.
Yeah,
and then that's a lot of cases.
That's the goal, but yeah.
I think it was in the first presentation that was placed at the building types, and it was specifically did not have the residential.
So there's a difference between the demonstration projects that we showed in the first presentation and then the goals of the whole project. So the whole project has the 4 types, but because at the beginning of the project we needed to quickly find the number of buildings where we could do demonstration, there was no buildings available through the different partners that had a secondary system and were residential. So we have a case study that is residential. It's in Switzerland, but it only has taps. It does not have a secondary system, so we could not implement the controls that try to better balance the action of the secondary system and the TAP system, but we monitor it anyway, and it will be included in the reporting of the project. We also do some work on indoor environmental quality measurements. Yeah, but we cannot implement the NPC because there's no secondary system to play with.
You can always use heating as a secondary system.
Yes. But then the tenants may not be easily convinced of that. That's also a problem working with residential buildings. There's much more stakeholders to convince.
Well, regarding the design tool, I can imagine that just gathering of all the data and making it comprehensive, extracting the key components will be beneficial not only for designing geotabs, but for designing other things. Is there any effort to make it available, or are you trying to use it just for the geotabs and will be using REHVA?
Oh no, we're also collaborating in an international energy agency project called Annex 70 Energy Epidemiology, and there's a lot of partners involved there that are focusing on building stock analysis for different typologies, and so the more generalizable results will eventually be part of that work.
Is there any outcome to this Annex 70?
Also there we're starting the last year, so it's crunch time for that.
And it's a 4 years project.
It's a 3.5 years project. Yeah.
Do you have a clear view already on the minimum input data you would need for the early design stage too? For example, can you just work with monthly data coming from a monthly energy balance method in EBD?
Oh, we didn't even go that far. Like the input data from the project side would be really characteristics of the project, without having made any estimate of loads or load duration, or just really thinking, okay, what are we going to do? What does the project look like? A first sketch of the architect, then trying to assess those characteristics.
So it's mainly building geometrical data, the volume, the floor area, the location, the type of building, is it an office, an elderly home, the overall U value, glazing percentage, so the real very general data. And actually we combine those with, via the database, we combine those with all the dynamic simulations that we are doing in the building stock analysis. So you don't have to make a simulation, you can just give the input data and we find them the closest by building in our database that is then started from for the sizing. So that's why we vary also a lot of building sizes and shapes and these 3 ranges of U values and so on, to be able to find the one that is closest to what you need.
And that's actually one of the main goals of the project. We really want to be able to do this with as little information as this, because as Wim explained, the goal is to have some basis in the really early design stages where you don't have the time nor the resources nor the information to do much more actually. So you just want to have some early stage predictions, like in the range of this is what we estimate in terms of investment costs, in terms of sizing for both of the systems, the different components of the systems.
Somehow replacing the more than 2, 3, 4 meetings with all the stakeholders to convince them there's something in this concept that really matches with your ambitions. That takes too much time, and if you then have to prove it and have to calculate it, then really as a designer you say, why am I doing this? And you see the advantages are on several levels that you could call societal steps forward. That will use more the electrical grid. It could be greened faster than the other ways of heating buildings. So you have all those advantages, and you need a tool to bring them to the table in an early stage. When you go towards further stages and you have the EBPD, that is calculated, then you're even more lost. Because then you have to prove this does not work correctly for this concept. So we want to deploy it, that's the first thing, okay? And we don't want this to be built just on shoulders of diehards, because they will die after a while.
And just wondering, since you have these multiple buildings, are you just reflecting on, in this case, this hybridGEOTABS will deliver so much and will cost so much, or will you also look at other design features and say, for example, you should alter your window to wall ratio or U value, and you can come up with an even better design, which is even more cost effective. Is that also a way you will approach it?
Okay, there's a part in there on the building level that will be feasible with what we do here. We need some set point adjustment then, I think. But certainly on the basis of the cost data, on the experience out of other projects, it's not only hybridGEOTABS that the designers or the practitioners do who are in the consortium. They're not building their business on hybridGEOTABS. They're doing a lot of energy concepts. So we have the data for the different concepts so that we can compare. That's what we try to do.
And for the building, you could change the property to yourself to another amount of glazing or another insulation level, and then we'll find again the building that is closest to your demands, and you can compare. In one case you might result with more geotabs or lower costs or higher costs than in another one. So in that way you could... No, within the tool it search what is closest to what you want, but you can think yourself, okay, if I make my building, if I change the orientation, if I do this or this or this, you can play with the parameters and we'll find the other building in the database that is closest to that. Because for each geometry we have all these variations, so you can actually start playing with them.
Also, there's a sensitivity analysis that you can do that basically is provided because we have the information available. But further to your point, it's actually a conscious choice not to just do an optimization, because then it's really restrictive on architecture. And so to come back to the very first question, the goal of the project is to demonstrate that every building deserves a part of hybridGEOTABS. And so also, if it's not the best glazing percentage, but for some reason the architect wants this, then you should still be able to provide the good information for that.
If you optimize the building design towards geotabs, then you'll have an ugly building. And probably not comfortable on all comfort issues. So the daylight and so we've seen examples through the past 2 decades. So that's not the aim anymore. On the other hand, and that's maybe an answer also to the first question of the Mr. there, is that if you use a geotabs, you'll have to do it right from the beginning. And it's an integrated design, an integrated approach. Architects like that. Like, it's an integrated design. They love it. They don't know what it means, but they love it. So you already you integrate in your building design a part of renewable or potential renewable for the future, depending on the electricity grid. So once this is in there, you can upgrade it later. So this is one of the main reasons that you don't only put a building, you are compliant with the EPBD, and then you have a minimum share of renewable, you put some PV on the roof. That's not the way to build the future. So we would like to have the integration and the affinity for integrating such systems very early in the concept approach.
I have a question about VCM.
Yes, please.
3 small questions. You said, or you showed that the temperature distribution you have, the drifting, let's say, with the PCM is larger than in the other cases, slightly.
In the air case.
In the air case, yeah. And you also showed that the capacity for heat absorption is lower. Has this to do with the power density of the PCM?
It has to do with very high cooling load, like off the room, and then maybe not enough PCM amount itself. So
Are the thermal conductivity is too low?
right, so that's another issue. But so
it's an important issue.
yeah, I mean it's one of the main problems with the PCM is that. But in this case, we did 2 cases. So we actually did this study just when we were, let's say, in parallel when we were constructing the panels. So as the material, the PCM itself, it has 0.2 watt per meter Kelvin. The one just like raw material itself. But we used in the simulations 1.2 because in literature we found a similar panel construction. So we said, okay, well, this structure that, because they had also some metal panels, fins and so on, it's very similar to this structure. So we said, okay, now we will go with 1.2 watt per meter Kelvin. So it's increased and we could actually see a lot of difference. But the problem is, this room, as I said, it's 53 square meters, and these simulation cases were for 24 occupants, so it's about 2.5 square meter per person. It's very, I mean, normally an open plan is like 10. So, and it was 50%, so there was some limitations
the worst
there.
case simulation.
Yeah, yes,
No.
yes.
And then regarding simulations, the operative temperature, we usually say it's the average of the air temperature and the radiative temperature. Does this still hold for TAPS or PCM ceilings? Can we still say it's just the average of both?
Well, average is kind of simplified actually, because normally you should take into account the convective and radiant heat transfer. So, or the coefficient.
You do, or you also just take the average?
No, we did we basically used the output from the software, but the software uses the ones with the heat transfer coefficient. So the software does not automatically do the average.
I'd be interested to see the results.
Yes.
What's then the weighting factor for the two components? And regarding the heat transfer coefficient you have from your ceiling to the room, is there any new insight?
Yes.
Okay.
Yes. I just no, but you mean for the ceiling cooling case, just for me to understand, or
for the PC?
You mean but from the surface to the room, right?
Yeah.
So yes, and the update or the new insight is that it's not directly related to the project, but it's related to something else. So for the radiant systems, and if you look at the heat transfer coefficient, it's what you need to provide to the room or what you need to remove from the room is actually independent of the rest of what's happening in the back of the surface, because the heat transfer, let's say, interface is the surface. So you have, let's say, the room side, which is interacting with the surface temperature and, let's say, surrounding air and the other surfaces, and there's the rest of it, which is the room side. Then it's important if you have radiant panel or tabs or other systems. So in this case, we basically treat it as a normal radiant ceiling panel. So it would, under ceiling, let's say ceiling cooling conditions, it would be, let's say, just 11 watt per meter Kelvin. But then it makes the assumption that there is natural convection, because then normally out of that 11 you can say, okay, 5.5 is around radiant, and then the other one is, let's say, the convective. Now, two things, because the first one is that makes the assumption, as I said, that there's natural convection. So if you have a diffuser that could be, let's say, a linear slot diffuser or something else, if that blows, let's say, the air along the ceiling, then it has the potential to, let's say, to move it to the forced convection zone. So you will have a higher, let's say, higher heat transfer coefficient. And that is something we want to try in the climate chamber experiments. Because in the climate chamber right now we don't use any ventilation. It's not realistic, but we first want to know what the PCM panels can do, and then we will look into different cases with that. The second point was that we, as a part of a separate project, we recently did a review of surface heat transfer coefficients of radiant systems. So for floor, wall and ceiling, and all for heating, cooling applications, because our feeling is that it's very important for radiant systems, because it's as I said, it's the interface between the surface side and the room side. but we kind of have the feeling that it's overlooked a little bit, that it's just taking for granted whatever and simplified a little bit. So we did that, we looked at the standards, different studies, guidelines, because not everything is the same, and we see that depending on which application you use or which coefficient you use, there could be quite high differences, which is, I mean, expected, but it was not quantified before. So, but in the paper we kept it to natural, because if you get into force, then it's like another world. So we didn't move that.